Hello. Welcome. If you expected this, you're in the right place. I'm Jonas, and I'm going to talk to you about what I spent the better half of a year doing, which is building an operating system that runs WebAssembly. Very quickly, this is me. Whatever, you can read it. Favorite artists: Vampire Weekend, Wolfpack, Gustav Mahler. Boom. To the point. If you forget everything that I'm going to talk about, right? I want you to see those two things and kind of marvel at it, right? That one and this one, right? That's the Apollo guidance computer, and this is a Milk V Duo. And this cost me €4, and it's widely more powerful than that, right? Which I find that incredible, right? Like, insane. It's so cool, right? There's I have a better picture of it as well. Better in some regards. And to me, the question is really why? And what we've seen over the years is that it turns out, hey, if I can put a thing on the moon, and it does that by itself, which, if you know the history, it didn't, whatever, then that's really useful, right? That's something that we want more of. We really want more of, and we've seen that, right? Like, computers are everywhere now, and so the hardware designers were kind of at a problem, right? How do we make the thing go faster, right? Like, I need more of what we have. And at the start of it, that was, making the clock speeds higher, putting more sort of compute into the same cores, single core scaling, right? The problem with that, we quite quickly reached the end of that. The problem is that it's very expensive, and also heat. Turns out, if you do things, it heats up. And what we ended up doing is, instead of doing the one thing faster, we started doing a lot more of, easier things. GPUs, best example, right? And or a SIMD, for example. And SIMD is actually, quite a good example of what I mean, because it sucks, right? It's very difficult because we, as meat machines, are really, really bad at parallel thinking. Right? We like, sequential, nice, it's easy, I kind of think about it, right? I do one thing, I do another thing, instead of trees and stuff like that. And here's some science to back that up, right? We've seen that even while transistor counts are linearly rising, the single thread performance in blue kind of plateaued off, right? Single scaling instead. Instead of, what we do is the black thing on the bottom, right? Like, we have more cores, we do more things. So that, right? Oh, and by the way, if you, have any questions or anything, we have plenty of time. I don't have that many slides, so just raise your hand. I don't want to, it's boring, right? Questions at the end, boring. Ask away now. Yes, well, that is the heat problem, right? If you increase the frequency of your cores, then it makes them way hotter, to the point where you really can't, right? And what we're seeing right now is sort of we're going back in clock speed, right? Cores are getting slower because we have such a big problem with heat. And if you do memory layering and three-dimensional dice, it gets even worse, right? Heat is sort of the big issue, and yeah, clock speed is sort of big factor of that. Right. That. Another thing that sort of I care about a lot, and that came up, is cybersecurity, right? I'm probably, don't really need to tell you about it, but it's important, and it's only going to become more important, as we move into the next 5, 10 years, whatever, right? And both of those things is kind of where existing, operating systems are kind of struggling at, right? Scheduling in operating systems is still very much stuck in the kind of like symmetric multiprocessing. Like you have a few, 4, 8 big cores. They, struggle with like efficiency cores, or what we're seeing like specialized computing units, right? Like a specialized coprocessor does something, or like maybe you mix like ARM and RISC-V on the same SoC and like have to get like the benefits of both. But like that is something that traditional like Linux, for example, really struggles with. And then cybersecurity, like same thing, right? I don't know. I'm not happy with the current state, but that's cool, right? Like that's very exciting. That's something we can solve, right? Like that's a problem to be solved, and this is sort of why I started that, right? And so I realize like my left alignment is kind of like I'm always in the way. It's great. Anyway, K23, that's the project I've been working on. Sort of self-funded that like for the last half a year. And the idea is really that we want, I want to try something that solves those problems. And I really think WebAssembly is kind of, well, yesterday I said it's both important and very unimportant at the same time. But it's important because essentially what WebAssembly allows you to do, if you switch from ELF or PE, right, like on Windows, to Wasm as your binary format for your programs, right? What you get from that is like you get more knowledge about your program, right? Like suddenly we have like defined linear memories, we have tables, we have like functions, we can sort of all inspect that. We get like, of course, the sandboxing. And then it turns out like having a JIT compiler in like, just at your disposal as an operating system is incredibly powerful. We can do stuff like, if I'm under memory pressure, I can generate code that consumes less memory, right? Like I can make my programs consume less memory. Or, the example I mentioned, if I have an SoC that has both an ARM and a RISC-V chip in it, like I can just do that because I have a compiler at my disposal. Even if like for example, someone were to like solder a different chip on the SoC on the fly, I could just like generate new code if I wanted to, right? So having a JIT compiler, incredibly powerful, very cool, and that sort of leads to an architecture where essentially you can think of it. Kernel, like hardware at the bottom, right? And then you have your lower level kernel functions like virtual memory. And on top of that, essentially everything is WebAssembly, right? I always sort of explain it in a way like you all are all familiar with like traditional Wasm deployment, right? Like say like Wasm time, if you're libc, all your Rust stuff, Linux, right? And then drivers, right? And so you take that stack, and then you just sort of take all the layers out, right? Like, and collapse your stack to where it's just like the operating system is the WebAssembly runtime, right? Yes? What do you mean exactly?
Is it a conceptual kind of thing that you do scheduling in a WebAssembly module?
Yes, so I want to do scheduling also as a pluggable component. I think that's very cool, right? Say like normal server environment, you have one scheduler, but then you kind of move into like an RTOS, like real-time OS situation, and you just switch out the scheduler because it's a different component. That's something I wish I can try at some point for sure, because it's very interesting and very cool. The problem is that scheduling is like very deeply ingrained, at least like right now, into like what you do, right? And so kind of that, mostly it's just hard to factor it out into like a component. And I have a lot of like stuff to do, and so that's kind of why I drew the line at that point, in particular like scheduling. But a lot of the sort of architecture is, it's a microkernel, right? So essentially, I try to have the kernel be as slim as possible, which I find, I realize is quite funny because like, you have your very slim kernel and you put like a whole compiler into it. But hey, the idea is to have like a very thin sort of kernel, right? And then everything on top of that is like WebAssembly, right? As much as possible. And whenever it is like feasible, I want it to be WebAssembly. If it's not, then maybe that's for later or for not at all.
Yeah, the question boils down to what would it take to make it feasible for even going lower?
What? Yes. Well, I will.
Is that a conceptual problem of maybe WebAssembly limits from its cost perspective?
Right. I will get to that. There is limitations in WebAssembly, definitely. I mean, I can also talk about it now. Doesn't matter. Whatever. I like that. This is cool. So, what I really want, right, is to have even like drivers implemented in WebAssembly, which that is tricky to do. Mostly because like you need very like tight control over the memory, right? Like sort of I need to have like a specialized region of my virtual memory that is mapped to like my UART output or my whatever. And right now that there's no such thing in WebAssembly, right? Like you just ask for a linear memory and you are provided one. And there's no control of, like, for the WebAssembly module to tell the runtime, hey, I actually want this to be mapped to like a special place in memory. And then the other one is memory ordering, where you need like volatile memory ordering if you do any kind of like writing to memory mapped I/O, right? So if the memory I have and I want to write to as a driver, right? That always requires like volatile access because it's I'm just writing to a device essentially, right? Like I'm just writing ones and zeros to like wires. So the WebAssembly like memory ordering that is sort of assumed and baked into it by default kind of like is a bit at odds with that. But honestly, like I'm willing to just ignore that, right? Because at the end of the day, like yes, having this microkernel is cool to where everybody could be writing a driver, right? You could be driving, you all could be writing drivers for this operating system, right? Very easy to distribute. But realistically speaking, like who's going to do that, right? And the few people, probably just me, forever, that will actually do that, just have to be careful about how to do it. And actually, sort of to get to the how you get a linear memory that is actually mapped to some specific point, the way I solve that for now, in a prototype, is that I just have a sort of special naming convention for the linear memories, right? Like I import a specially named memory from the host, and then the host just knows what to do with that, and then give me the right kind of memory. Not awfully convenient, but it works. Definitely, though, an area where, like, there's the WebAssembly, what's that, memory management proposal, I think is called, right? Definitely an area where, like, improvement could definitely happen. All right. This is more what I want, right? I think the future that we're moving towards, right, massively parallel, requires us to also respond in kind in software, right? Like make our system benefit from this kind of like many cores, many cores. And again, like WebAssembly is quite nice for that, and I will get to why. Just I have a nice slide that just sums this all up. This is the idea, basically. This is the plan. It's written in Rust. By the way, I don't a lot of people like put that front and center. I don't really care about it. I like Rust, but it's a language. And one thing that sort of I put in the slide just this morning actually because of yesterday is debugging, profiling, and observability, which I realized I was always like, oh debugging WebAssembly, that is so easy. compared to like the insanity that is debugging like low-level like code in QEMU. But I realized that it's actually not great, but we can do much better. And I think like one area where I want to put focus with this project is just like driving debugging, profiling, all of that with WebAssembly more, because it's not only interesting for an operating system, it's like it's broadly useful for us as an ecosystem and as a community. And then, yeah, maybe interesting like Arch64, RISC-V, and x86 is the targeted, instruction set architectures, the targeted computers. With like x86 sort of being at the end, because I don't really care about it. Which needs to lead to like, this is all cool, right? This sounds good, but what's the project actually like right now? And I made a bunch of progress over the last half a year that I've worked on it full time. We now have full like the virtual memory subsystem, like mapping memory, getting memory, all of that works. The scheduler is set up. It's based on async Rust, right? It's sort of a Tokyo kind of thing. not really, but kind of. And we also have support for I/O, interrupts, right? Like you can subscribe to an interrupt and then async wait for it until it happens. And you can also have timers, which is just an extension of interrupts, but in a nice sort of package, right? You can wait for timeouts. That's quite useful. And then the sort of part that's probably interesting to you is the WebAssembly engine, right? And that is built on CraneLift, sort of architecturally similar to Wasm time, just because it's the same code generation backend. And I looked at it a whole bunch, but it's sort of custom, and it actually needs to be, because you do all of the like interrupts handling, right? And all of that is custom. And then, yeah, so almost all of Wasm MVP should be supported, except for one very important part, which is host functions. That's why I'm also saying like it should be supported, because like the test runner for the spec suite requires host functions, and I don't have them right now, and so I don't really run any tests aside from like the one I have myself. What?
What's the difference between an import and a host function?
So importing from other WebAssembly modules is much easier, because all of the machinery for like having the function pointers in the VM context and like managing and moving those around already has to exist anyway. But if you want to import a Rust function, from the host environment, then that requires you to like set up, a whole like fake VM context for the Rust side, and then do and manage that. And I have a prototype. It's in a PR. It doesn't work yet, but yeah, it's actually I was surprised myself. It's like substantially different to just regular Wasm imports. Function imports. But yeah, so imports and exports, linking, all of that works. And I will get to it and show you how that actually looks in code in a demo. But yeah, so host functions missing. I don't really have any drivers right now to speak of, and then a million other things, right? It's an operating system. It's never done. Like I can work on this for 100 years and not be done, probably. Sorry, I have this one. Why not? I want to sort of emphasize one thing, and that sort of is important for the example I'm going to give now, which is the microkernel architecture, right? That quite sort of naturally falls out of WebAssembly, but I want to, just so we're all on the same page. The idea of microkernels, right, is that, as I said, like you keep the kernel as thin and lightweight as possible to reduce the attack surface of the kernel itself. And then you layer the sort of modules on top of that. The advantage of that is that all those modules you can manage individually, right? Like you have very sort of tight control over what parts of your code are on your machine, what gets run, and then you can potentially even sandbox them, right? Like you have very strong isolation, very high reliability. That's why people like microkernels. The problem with them traditionally, and that's quite crucial, traditionally the problem with microkernels is that all of these components, nice, cool, works, great, but it requires message passing, right? Like it requires the components to send messages, like through like a ZBus, for example, in Linux, like messages between the components. And that always requires a round trip through the kernel, right? If like component A wants to talk to component B, right? Say like, hey, I'm a program and that's the file system, right? And I want to read a file and I need to send a message to the file system to retrieve data, and then it sends that back, right? And that you can see why that is kind of inefficient, right? Because it requires like 4 syscalls, right? Like 1 to send the message, 1 to send to the other program, 1 back, and like 4 syscalls versus what you would have in Linux where it's 1. Right? And so traditionally, the problem is that that is just performance-wise not competitive. You cannot get it to go fast enough, like people have tried, to where it's good enough. And I want to sort of give 2 examples of that, sort of more in detail, because that is sort of the core outcome of what I've worked on. And let's start sort of with a quite simple example. It's just like get random, right? I want to get a random number or fill my buffer with random bytes. But that's just a syscall, right? I ask the kernel, hey, can you give me random bytes? The kernel's like, sure, yeah, here you go. And how that looks on a stack, right? This is a stack. It grows from the top. Stack frames will get put on it, and then at some point it reaches the bottom, right? You kind of fill it up from the top. On the left, like in blue, that's my program, right? And it now wants to do a syscall, right? It tells the kernel, hey, give me random bytes. It does that, and then the kernel does its thing, has a separate stack for it because it needs to, right? Like kernel stack, user space stack. It returns, and now we can use a random number, right? That's Linux. Now, with WebAssembly, it looks like that, right? We have a function, and then we ask the host, hey, can you give me random numbers? And the host function that we just imported gets run on the same stack, right? It returns, we can use the random numbers. More complicated example, we have a file server, right, that sends out files over HTTP. And we have the file system, in a microkernel that would be its own component. And we want to read a file from the file system, right? So it's program A and program B. Totally different. They do not trust each other, just like random programs. In the middle, we have the kernel. To the right, we have the file system. So program A, the web server is like, OK, I'm going to ask the kernel to ask the file system to give me the file, right? The kernel does IPC dispatch, right? Finds out to which program it needs to route the request. Finds the file system, sends the message, right? And then the file system does its thing, whatever file systems do. Returns, IPC routing needs to go the other way then. Return, boom. We can print our file or send it. Now, Linux. Here's how that looks in WebAssembly. We have a function, right? And then we call out to the file system. Because when I have a component or a module in WebAssembly, right, I just import a function from the other program, and then I call it, right? And then we can send it off, whatever. Crucially, this, right, would be insane to do in a traditional operating system, right? Like this would be wildly unsafe because I'm giving my sort of private stack data, which is usually like the most sort of relevant, like the most sort of at risk of like compromise, right? Like the stuff I have on my stack, I'm giving access of my stack to another program, right? I have a random program I do not trust mess with my stack. That's like, that would be insane to do. But because we are WebAssembly, right, and the stack is managed, WebAssembly programs cannot interact with the stack at all. This is fine. This is safe. And the cool part about this is that, you know how I told you, like, you know, the round trip, the Wasm round, the IPC round trip for microkernels, that just goes away, right? Because I have my program A, and it wants to do a request to another program, but it just like, it imports a WebAssembly function and just like runs that function as if it were any other function, right? And so this is what I'm excited about, right? Like this is the cool part, is that this is microkernels, the holy grail of microkernels, right? Like this is microkernels without the performance overhead, right? This is sort of what people are chasing. And it's possible, again, because of WebAssembly, more because of the JIT compiler, but because of WebAssembly, right? This is what I'm excited about. All right. Demo time? Want to see some actual code and not ugly drawings? Yes. All right. Let me try to move this to where you can actually see it. And also, yes. There is probably a better way to do this. I do not know the way. It's all right. OK, so this is the repo, right? And if we go into kernel, and then kernel source, Wasm. Oh, let me show you. Actually, let me show you the WebAssembly first. All right. So the test case I'm going to show you is it's two WebAssembly modules, right? It is this one, which is a C++ Fibonacci numbered, calculation function, very simple, that I compiled to WebAssembly and then took out the WAT from it because it's easier to manage. This function is not really important. It just does things, and I can test it. And then I have another module, right, that I don't think I can increase the font size. No. But OK, so one function, or here we import that Fibonacci function, right, and then we just test it with a bunch of inputs, right? Like we just throw numbers at it and test it. I'm not sure how in yes. Better? Yeah. So, this is the check function, right? It just like calls the Fibonacci function, and then if the output is not what I expected, then it just traps, right? Very simple. And then we just test it with a whole bunch of inputs and see that actually, yes, it generates the right numbers. Which this is very trivial, but it's exercising like the linking and the function calling, right, and all that. So because like real WebAssembly components, the cool stuff, isn't supported yet, I have to like do the linking myself, if I can find it. Yes, yeah. So I hope this is, can I zoom in a bit more? So here, basically, we load the first module, right? We load it from bytes, then we instantiate it, and then we define it inside of the linker, so it's available, right? And then we, do the same thing for the second module, get, a function, the function from it, and then, call the function. That's sort of all it does, right? Yes? No, actually, it's kind of like that was like when I raised sort of my idea with them 2 years ago, almost. That was like part of the discussions, I think, kind of like led into the no STD support now, because I actually had to like, the crane lift backend, I had to like port myself. because it didn't support. It claimed to support no STD, but it actually didn't. Not a big deal, it's just like a port, whatever. But it's kind of interesting that all of the stuff that I want to do with the WebAssembly runtime is actually what Wasm time no STD does not, right? What they do is they do software traps, right? So you don't rely on hardware traps and a whole bunch of other things. But kind of the whole point, why I want this to be an operating system is because I want control over the hardware traps, right? I want that. That's what I need. And so in a funny way, it's kind of like actually like the opposite of what I want from it. But it's good. I think it's useful for people, just not for me. Okay, so very simple. This is all it does, right? Defines two modules, then calls it and has like a call chain. Cool. So let's do this. A big recommendation if you want to try it. Maybe it's very easy. It should be very easy to get started. Just clone it. You need NICs because on some Linux versions, the QEMU that's in sort of the package repo is very outdated. And so if you want to try it, use NICs because it has the versions of QEMU that actually work. You do that, and then you just type just run. I can also make that bigger if that helps. This, like that. And then, boom, we boot it, right? Let me see. I want to move the interesting stuff up. Yeah. So we're booted into like a very easy, very sort of simple debug shell. It doesn't support a whole bunch of things. You can panic the kernel. You can crash the kernel. You can shut down the kernel, but you can do one interesting thing, which is execute the WebAssembly test that I just talked about. Right? If we do that, what you will see is that. Right? And what just happened is that we compiled everything. Here you can see like the debug output, right? Like this is what CraneLift generated, a whole bunch of machine instructions, and then you can see sort of this is a debug dump of the VM context, right, that manages all the state of your module and all the pointers and the function references, and then it just runs it, right? And one thing I'm quite sort of fascinated by, as sort of didn't really plan for it, but kind of turned out to be that way, is that this is all like debug mode with incredibly many debug symbols and quite slow, and it's still very fast to start up, right? Like the startup times, because you're not booting a big kernel, right? Like it's a very thin kernel. You just boot into it, and it's very fast. It's kind of interesting because WebAssembly is also very fast to boot, right? Like it's like a perfect fit. It's like a fast starting system that just like from metal. And like keep in mind, this is like a fully cold start, right? Like there are no caches, there's nothing, The compilation has to be done like from scratch and everything. And yeah, kind of interesting. Any questions, any comments so far before I move on? No. Did I go too fast? No. Yes.
So this is like a consciously naive question, but what's stopping sort of a microkernel architecture from having a separation from the kernel file system and sort of having a bunch of user space VFSs essentially talk to each other? So for something like reading on disk, right? You could, in theory, right, have a component that's like strictly like a home directory, or strictly like the movies, etc.
Yeah.
Essentially saying, I'm not giving you a complete partition, but like you can access my memory arbitrarily. However, all you're going to get is a bunch of movies.
Yeah, that's a very good idea. I mean, totally, that's one thing I think why this is kind of cool, right? Like that you can do that, right? I can give like programs, similar to, so what I think, and we see that with like, Windows, I forget the name, the new Windows application system where they sandbox your app, right, and you get sort of your own subfolder. I think we're going to move into a future, sorry, what? UWP. Yes, exactly, UWP, yeah. And we're gonna move into a future where, similar to iOS and Android, right, even on desktop, your app will be, very siloed, right? Like having one sort of big shared file system, I think that's sort of a relic of the past. And we see that with macOS as well. Like big operating systems are already moving that way, and I think it makes a lot of sense to have like instead of one big file system, maybe, and it might be under the hood still like one big file system, right? But exposing that into like sort of like bubbles of data that you can like access by movies or whatever, yeah.
In a more practical way, so is there an example of a microkernel architecture ignoring WebAssembly where there are instances of sort of components talking to each other strictly in user space and essentially then agreeing to do a syscall? Right, because some of the problems is that the components talk to each other when they have to do this round tripping, right, into kernel space.
Yeah.
Is there, in theory, can you do like some sort of consensus, like essentially do the IPC, do the message passing, and then say, okay, we together essentially are going to do this or these series of syscalls?
That's interesting. I don't know. So most of the microkernels, the way they sort of designed is like a very simple server-client model, right? Where if I'm an IPC sort of program that exposes something, I'm basically a server, right? And I just have a function that gets called whenever I receive messages. And then the clients just like, HTTP fetch, just send messages. I don't know if, that sounds interesting, but, maybe. Okay, yeah. Yeah, so, I think we are all excited about components probably, but sort of I want to emphasize that a bit, that when I read the component specification, sort of the first draft or whatever that I saw, like I was like, this is made to be an operating system, right? Like this is, and like you can make the case that like any WebAssembly runtime is sort of an operating system, right? In a way where, but I was like, this is made to be an operating system. And so what you can see sort of on the side, like that's one example of how an application would kind of look, right? It's like you have your root application that does something useful, and then it might need to do like network communication. It imports like WASI sockets or WASI HTTP, right? It might need to do some file system writing. It imports WASI FS, right? And under the hood, those implementations themselves go out and like import an NVMe driver, right? Like import like a time driver, import the network driver itself. What's cool about that is, think about, with Linux or any other traditional operating system, when I install the OS, right, I get every driver that exists, right, and that the maintainers like chose to compile into my distribution, because I have to, right? Like it's like one monolithic thing. But with components, all I need is sort of this base set of drivers that gets me booted and access to the network, and I can just fetch only the things you actually need, right? Like in this sort of scenario, you will only ever get the drivers and the packages and like sort of all the infrastructure of your system that you actually need for your particular hardware, right? Which I find that quite interesting. And then, of course, you can compose it. You can like, just import the interface, and then the user or the runtime can decide which component to choose to implement that, right? And at the end, sort of what you see is like a microkernel, right? And that's what I'm working towards, is a microkernel that has like full NixOS, right? Like strong hash-based dependency tree management, but down to the driver level, right? Which that is like great for reproducible builds, right? Great for reliability. You can just roll back, and it like includes the drivers and all that. And yes, I said like fetch only what you need. Yes, I think I went quite fast. How much time do I have? I don't know. Doesn't matter. Because coffee. That's it. Thank you. And happy to chat after as well, hear your ideas. Yes, if you want to see the GitHub, then that's there as well. All right.